screen.
Wonderful, wonderful. So our next speaker is Professor Maria Chernyakova from Dublin City University in Ireland. And Professor Chernyakova is going to speak about broadband emission from gamma ray binaries with a radio pulsar. Professor Chernyakova, I'm going to give you a 20 minutes, I'll give you a 2 minutes to go sign, or I'll speak up and say that, but please take it away.
Yep, thank you very much. Unfortunately, I have no idea why my camera is not working, because I was using Zoom the whole day today and everything was always fine. But well, the main thing that you see my slides.
Yes, we do. We do.
Yeah. So I think, okay. So thank you very much for inviting me to give this presentation. And we have heard today about lots of very different topics, and I'm happy to tell you about the physics, which is very close to my heart, to speak about the gamma ray binaries, and in particular gamma ray binaries with a radio pulsar. So yeah, my name is Maria Chernyakova. I'm from Dublin City University, and this work was done in collaboration with my colleagues, in particular with my PhD student Sam McKee, and also Denise Malashev from University of Tübingen, Brian Van Solen from University of Free State, and Dr. Pere Blay from Valencian International University. So what is it all about? So this beautiful image, if we can see it if we are lucky and we have a clear sky. But what will happen if we have not optical but X-ray vision? Well, then the situation will change, and the number of stars that we will see will be somewhat smaller, but still we'll see lots of objects. And in particular, if we will be interested in the galactic objects, we will find out that the galactic X-ray population above 2 keV will be dominated by the X-ray binaries. At the moment, there are known about 300 X-ray binaries, which can be split in the low mass X-ray binaries and high mass X-ray binaries. In high mass X-ray binaries, the black hole or neutron star is orbiting around a really massive star or B-type star. Typically, it's about 30 solar masses. And as I said, that the orbit object, it can be a neutron star, and we now know about 20 black hole systems. So what is the origin of the X-ray emission? Because if they are able to emit the X-rays, it means that they are able to accelerate particles to high energies, and the main energy in this source case, it's produced by the release of the gravitational potential energy of the accreting matter. And what will happen if we go look into higher energies? So if we, by any chance, will have a chance to have a TV vision, then the situation will be changed. Nowadays, with HESS, MAGIC, VERITAS, TV astronomy, it's a real astronomy. We see lots of sources, but if in X-rays, galactic sources were dominated by the binaries, at TV sky, we will see only about 10 sources, not more. In all these sources are high mass binaries. In all these sources, we have either O or B-type star, but actually the compact object, whether it's neutron star or black hole, is not known in practically in any systems but 2. So in 2 systems, PSRB 1259-63 and PSRJ 2032 plus 4127, we know for sure that the compact object is a neutron star. It's not only a neutron star, but it's a radio pulsar. So it's fast rotating neutron star, which is producing a jet, a wind of the highly relativistic electrons. And what happened? We remember that this pulsar is not alone. It's a binary system. So there will be interaction of the pulsar wind with the wind from the BE star. And this collision of these winds will produce a system of 2 shock waves. And the particles beyond the shock, they will produce synchrotron emission, they will produce inverse Compton emission, and we will be able to see the emission from this system from radio up to very high energies, up to TV energies. If we look at the somewhat lower sky, at the GV sky, we know we can see such systems as Cygnus X1, Cygnus X3, and these are famous X-ray sources. And in this case, we have a compact object where we have the accretion. Accretion is producing a jet, and then we are able to see GV emission. SS433, it's also a microquasar, and recently HAWK was able to detect TV emission from SS433, but it is very standalone case because the TV emission is seen not from the central object, but rather from the lobes. What about other gamma ray binaries that we know? At the moment, we don't know whether there is a pulsar there, or accreting neutron star, or accreting black hole. And in principle, it's a quite important question whether the accretion can accelerate particles up to TV energies. What it can be, it's quite plausible that actually there is a radio pulsar in there, but these systems are much more compact. So it is possible that all the radio pulsations are just absorbed and we have no chance to see it. So what I will speak to today in more details will be these two systems, systems where we are sure about the nature of the compact source. And if we study these systems in details, maybe we'll have some idea how to find out, how to prove maybe in the indirect way that the pulsar can be hidden in other systems as well. So first of all, I will start with PSRB 1259-63. It is the most known system. It was the first binary system which has been discovered at TV energies. And in this system, a radio pulsar, millisecond radio pulsar, is orbiting along very eccentric orbit around the B star. The orbital period in this system is 3.4 years. So in principle, this is quite ideal period because it gives us a chance to organize observational campaign, to make the observations, to analyze the data, to publish the paper, and to prepare for the new periastron. So in this system, the companion, or optical companion, is a B star, and B star, they are known to have a disk because they are rotating very fast. So the wind is pressed to form the disk around the star. And in this system, the location of the disk is rather unusual because we know that it's lying not in the orbit of the rotation of the system, but rather it's inclined. So in this sense, pulsar is orbiting, crossing the disk twice. As soon as it is approaching the disk, then it goes away, then it crosses the disk second time and goes away. So actually this system is a perfect laboratory to study the property of the interaction of the pulsar wind and stellar winds. If we look in the light curve on this system, so here you see the light curves at different energy bands, starting from the GV, X-ray band, radio, and optical. So both in X-rays and in radio, we see that there are two peaks, and the position of these two peaks corresponds to the moment when the pulsar is crossing the disk. If also we look in the details of the spectrum is nicely described both in radio and in X-rays by the power law, and we see the softening of the X-ray spectra during the moments when they cross the disk. So here the spectral index is about 2, around the periastron is about 1.5. Also, what was very unusual in this system when we start to observe it at GV energies with Fermi satellite, it reveals a huge flare. The flare happens already when the pulsar goes back, or it already crosses the disk for the second time, and actually no one was expecting anything around this time, and we don't see any counterpart to this huge GV flare neither in X-rays, you see that here nothing is happening, nor in radio. Again, at the moment of the GV flare, nothing is happening. The only place system where something is changing is actually optics. So in optics here, you see the equivalent width of the H alpha line. And what we see that at the moment of the GV flare, we have the disruption of the disk. So again, we cannot say for sure whether it is disruption of the disk which is causing the GV flare, or is it the GV flare which is causing the disruption of the disk. The only thing we can say that these two events are probably linked. And why I said that it's a huge GV flare? Well, first of all, you just see that it's much higher than it was before. But then again, what is the energy that we have in the system? The main source of energy in this system is the spin down luminosity of the pulsar. And in 2017, we have seen that we have the flare is not something monolithic. Instead, it's rather consists of the subflares. So here you see one-day beam light curve, and these one-day beams in case is also composed of the subflares with the length of even 15 minutes. And if we calculate the luminosity during this 15 minutes flare, we will find out that it's about 30 times the spin down luminosity, which is huge, and it puzzles scientists for quite a while. And what I want to do now, I want to present you our model where we were trying to explain what's happening in this system. So here you see the sketch of our model. This is the orbit of the pulsar. This is the disk of the B star. And this is the structure of the shocks, which are formed due to the interaction of the winds of the B star with the pulsar wind. And the main idea of our model is that there are different regions where different populations of the electrons which are producing X-ray and TV, and electrons which are producing the GV emission. So what happens here near the cap, we have the pulsar electrons of the pulsar winds, which has been accelerated to a high energy at a strong shock. And X-ray and TV can be explained as a synchrotron and inverse Compton emission of the strongly shocked electrons of the pulsar wind. In its turn, the GV emission most probably is coming from the electrons which were either non-shocked at all or has been weakly shocked, and it will be inverse Compton emission of these electrons or Bremsstrahlung emission on the clumps which has penetrated into the winds. So here you can see how our model is trying to explain the data, and you see that it looks like the agreement is pretty well. And in this case, if you believe in this model, then the luminosity of the GV flares can be understood if you assume that the initially isotropic pulsar wind, after the shock, it is reversed, it is located into the cone, and we're just very lucky. Just after the periastron, the cone is looking at our direction, and what we see the observed luminosity. Okay, so this is about PSFB 1259, and recently one more system of similar type has been detected, and this is PSRJ 2032 plus 4127. Actually, this source was detected quite a long time ago, but it was detected by the Fermi as a GV pulsar. And the fact that it is a binary system has been discovered not that long ago. And the reason for this, that I told you that in 1259, the orbit is quite elliptical and elongated. But it's not that, here it's even more elongated. The orbital period in this system is around 50 years. So in this case, each periastron is really an event, one of a times to be observed. The last periastron happened in November 2017, and similar to 1259, the unpulsed radio, X-ray, and TV emission has been detected around the periastron. In GV, there was no difference, so at GV energy, we still see the same stable emission, and most probably just coming from the pulsar's magnetosphere. So what do we see in X-rays? You see here the swift observations, and you see that similar to the 1259, we have two peaks around the periastron. So here on the x-axis, I have the time, and here I have rather the orbital angle. So just to see these two peaks more clearly. And in green, I see the X-ray index. So a slope of the X-ray band spectrum hardens as the pulsar is approaching the B star, and it reached the value of 1.5. As for the hydrogen column density, we don't see any variation. So the model we want to propose, we want to say that similar to 1259, we believe that in this system, the disk is inclined to the orbit. And in this case, X-ray and TV emission are synchrotron and inverse Compton origin correspondingly. We assume that initially the electron spectrum has slope -2 with a low energy feature, break or cutoff. And in this case, there can be two scenarios. One scenario is a so-called cooling scenario, that we are starting with the monochromatic electrons with energy around 20 TeV, and they are constantly injected by the pulsar to the region where they interact, and continuous radiation losses, they modify the spectrum and form X-ray and TV emission. And you see this cooling scenario here with the blue line. Alternative possibility is acceleration scenario. In this case, we are injecting, again, monochromatic electrons, but at much lower energies, at energy about 0.1 TeV. And we start to accelerate this shock, and this will lead us to formation of cutoff power loss spectrum with a slope about 2, if we believe that there will be Fermi acceleration, and cutoff at around 30 TeV. And on longer time scale, the spectrum of the electron will be modified by the synchrotron and inverse Compton losses, leading to the observed X-ray and TV emission. So what can we expect in this case for the broadband picture? X-ray flux will be increasing as the pulsar is entering denser region of the stellar wind, and the wind-wind interaction region will shift towards the pulsar. The dip close to the periastron happens at the moment when the pulsar enters sparser regions of the B star disk, and the wind-wind interaction region in this case will shift further from the surface of the pulsar, and the magnetic field will be decreased in this region, and so you will have the dip. Again, when you have this dip in X-rays because of the shifting of the position of the interaction region, it means that this interaction region is closer to the surface of the star. And in this case, we can expect, in agreement with the observations, that we have increase of the TV emission. In the case of this PSR J2032, we cannot distinguish between this cooling and acceleration scenario. But if we assume, look what's happening in PSRB 1259, we will find out that it's only acceleration scenario that is able to explain what we observe. Because in this case, PSRB 1259 has larger size of the disk, so it leads to the high value of the magnetic field in the emission zone, and so you will see the corresponding softening of the spectral slope which is observed, and also absence of the TV counterpart of the GV flare in case of PSRB 1259 can be explained only within the acceleration scenario. So in this sense, comparing this behavior of these two systems, we believe that in PSRJ 2032, acceleration scenario is also more probable. So also we have optical observations of PSRJ 2032, and what optical observations can tell us about whether our model is plausible or not. So indeed, the interaction of the pulsar and stellar wind can be traced by the evolution of the H-alpha emission line, and tidal interaction increase the size of the disk. So you can see it here in the violet and green. You see that first, the tidal interactions leads to the increase of the size of the disk and the increase of the equivalent width. And then when we have the maximum of the electron width, roughly corresponds at the moment when X-ray hardens to -5. So the moment when we start—
Chernyakova, 2 minutes to go, please.
Yes, that's perfect, thank you. So at this moment, X-ray hardens to -5, so it's here. And this is the moment when we start the efficient interactions with the disk. After that, the external layers of the disk are destroyed, and this leads to decrease of the equivalent width. And this destroy of the disk is in agreement with the computer simulations. Here I show what is predictions of the hydrodynamical model from the Ko et al. In 2019. And you can see that in computer simulations, we see that the part of the disk is just removed. And this is exactly what we see in the optical data if we look at the evolution of the V over R data. So we just see that part of the disk moving away from the observer is just fully destroyed. And what happens afterwards, as we move further, a gradual increase of the disk after the periastron, again, due to the tidal interactions, and then the gradual decrease of the disk starts as the pulsar moves away. So this is what I wanted to tell you about these two binary systems. And in the conclusions, I just want to say that very high energy emission from gamma ray binaries is the result of the interaction of the relativistic wind from the complex star with the non-relativistic wind of the massive optical companion, or B-type stars. And I believe that gamma ray binaries are extremely interesting sources, and they are a unique laboratory to study the details of such interaction and give a chance to measure the various parameters of the stellar wind, geometry, density, clumps, and also to study the relativistic wind, for example, to determine the Lorentz factor of the electrons. A study of the gamma ray binaries with the pulsar allow detailed modeling, and this can be used as interpretations of such systems and to build models that can be applied to other systems to identify the nature of the complex objects. Broadband observations critical to study the details of wind interactions, and existing observations, unfortunately, are not enough to explain all the details of the physical processes in these systems, and hopefully future instruments like CTA will allow to study broadband spectral evolution of these systems on short time scales, which is really critical for testing the existing models. So thank you very much for your attention, and I will be happy if you would have any questions.